So students, will be continuing our discussion on 60 SRAM cell. In the last lecture, we have seen a 60 SRAM cell structure. Its hold operation, read 0, read 1 operation, and also write 0, write 1 operation of 60 SRAM cell. So we have completed the operation of 60 SRAM cell. Next, we are going to go for the different structures of SRAM cells. So we have static random access memory, which is your SRAM. So here the stored data can be retained indefinitely. We have a simple latch with two stable operating states. We have seen this today in the general structure, right? Now these inverters can be, this is the general topology of SRAM cell, okay? And this load can be either a resistive load or it can be a depletion load or it can be a PMOS load. That is a CMOS inverter. And we have chosen a PMOS load. Okay, we have not chosen resistive load SRAM, or rather it can be there, but we have not chosen it. Okay, we have, everyone has its own advantages. So there are two access switches here and here to connect the 1-bit SRAM. All right. So there are advantages and disadvantages. You can go through it, but not required. Depletion region also we don't have that. We have only full CMOS SRAM cell. That is 60 SRAM cell. This is also called as 6 transistor SRAM cell. So it has its own advantages that it is the most popular among the remaining topologies, and it's having the lowest static power dissipation. It's not completely zero, but it's lowest. It's not completely zero because of the leakage currents in the MOSFETs, and it has a very superior noise margin and the switching speeds are very high. Okay, that's why we go for a this full CMOS 60 SRAM cell. Now let us draw the structure of full CMOS 60 SRAM cell. Only in some books the names are given differently, but it's one and the same only. So let's for revision draw it once more time. So we have the two inverters. This is inverter number 1. Okay, and we have another one over here. The output of first is connected as input to the second, so here it is, and the input of first is connected as output to the second. Okay, then we have access transistors. Some books have shown it up, some books have showed it down. It doesn't matter, it's one and the same. So these are access transistors. Okay, this is word line, and these two are bit lines. So this is bit line, and the next version is BLB, bit line bar. Okay, then there are precharge transistors required during the read phase. So we can connect a precharge transistor over here. Which will precharge the bit line. These are pseudo NMOS transistors, as we already know. If we connect its gate terminal to the ground, then it's permanently on. So it will precharge the bit lines to VDD. And then we have a capacitance present over here, which are parasitic in nature. So CBL and CBLP. Okay, the naming can be different in different books, that's fine. This is M1, M2. In some books this is called as M3, M4. So here let me call it M3, M4, M5, M6. So this is full CMOS 60 SRAM cell we have just now covered. Okay, any doubts over here? So there are three operating modes: hold, read and write, which we have covered already. So now we'll see its design strategy. How do we design them? So designing means the inverter ratio we have to take care. That means W by L ratios of the individual transistors. Can we move ahead now and explain you all? Okay. So this is the same cell here, as I've told you. They have named it differently. Instead of calling it bit line, they have called it as column, bit line C and bit line C bar. But that is absolutely fine. Now these are the pull-up transistors per column. These are the pull-up transistors. We can call it MP1 and MP2. So MP1 and MP2 are the pseudo NMOS transistors or the pull-up transistors as shown over here. Okay. So this will pre-charge the bit lines to VDD for the read operation. And these are the parasitic capacitances. This is the word line which is shown below. As you can see, the numbering is different: M1, M2, M3, M4, M5, M6. Here M3 and M4 are the excess transistors. Only that much difference is there. So what are the advantages of full CMOS? So it is also called as 60 SRAM cell. Alright. What are the advantages? It's very low static power dissipation, high noise immunity, that is noise margins are very large, ability to operate at lower supply. Only disadvantage is that the cell area is slightly large and the latch-up phenomena occurs, which will lead to a highly large amount of current. Okay. So now we'll see its design strategy. What do you mean by design strategy? Meaning, when we do the read and write operation, there are certain criteria which we have to follow. Now let us understand this. This is called as design strategy. Design strategy means selectively selecting the W by L ratios of all the transistors are not the same. Not at all the same. Okay. So due to that, we have to be careful in designing these transistors. So I will draw again and explain it to you. See, this is the VTC curve of an inverter, V in versus V out. This is how it looks like. And in that we have a switching threshold. When V in was equal to V out or V out was equal to V in, this is called as a trip point or a switching threshold. Okay, and this is normally VDD by 2. So if the V in is less, to the left hand side of the trip point, the output will be high, and if it is to the right hand side, the output will be low. Okay, so this point can be over here also, it can be over here also, depending upon the slope. So this trip point can change. All right, so the two basic requirements which will dictate the W by L ratios of all the transistors over here are as follows. So we will study them one by one. Let's go through this operation. This is a read operation. Concentrate on this diagram now. Okay, this is a read operation. Basically we can say a read 0 operation. So basically a 0 is stored on Q. This is Q, let's say, and this is QB. So 0 is stored on Q and there is a VDD in QB. Okay, this is my bit line. Basically we can call it, this is bit line and bit line bar. Alright, so now how does this operate? Tell me. So word line is 1. So these are VDD as you can see over here. So word line becomes 1 means what? The M4 and M3 are on. Okay, so M3, M4 according to this diagram are on. Now since this is 0 at the storage node Q, it is storing 0. Which transistor will be on? M1. So M1 is on and M5 is off. Okay, so M5 off is stored, is shown in light color. Okay, dotted lines. And since this is VDD, QB is VDD, which is on? M6 is on. So M6 is on, and we have showed over here M2 is off. Okay, so basically over here we have VDD, and basically over here we have ground, almost 0 volt. That means M6 is on and M1 is on. So right now number of transistors which are on are M3, M4, M1 and M2. So these are the transistors on. Now what do we say for the bit lines? Bit lines are pre-charged to VDD. So these are already VDD before the read cycle. Before the read cycle starts, before the read access, your BL and BLB is VDD. Okay, so your BL and bit line bar are both logic 1 or VDD. Alright, so tell me now what will happen. I've explained all this. Now tell me what will happen over here. So we initially assume that 0 is stored in the cell. Okay, so voltage at Q is 0 and voltage at V2 is VDD. And BL and BLB is VDD. So what will happen now? Tell me. Come on. M1 and M6 are on. Both are on. Now what will happen? Tell me. Perfectly fine. CC will discharge via M3 and M1. Absolutely right. This will try to discharge like this. Yes or no? So that means what will happen now? Because there is a voltage difference between BL and Q. Here it is 5, here it is 0. So this voltage, the voltage at BL will fall down slightly, right? Will be less than VDD. Yes or no? It's written over here approximately equal to VDD but less than VDD. Okay. Similarly here what will happen? Here voltage at BLB is VDD and voltage at QB is also VDD. So will the capacitor discharge? No. The capacitor will retain the discharge. So VC C bar will retain the charge. Yes or no? So voltage at BLB will be exactly equal to VDD. Agree? Yes or no? Okay. So now this sensing, I mean it will be sensed by a sense amplifier. Now this will go to a sense amplifier as I've already informed you. This will go to sense amplifier and it will give the data output according to the whichever line is higher. So BL is less than BLB, so it will give the output as logic 0. Since BL is less than, voltage at BL is less than BLB. Okay, this will happen. This is the problem, right? But you're effectively designing, blindly designing the W/L ratio same of M1 and M3. Will it work if I keep M3 and M1 same? Same means whoever is having W/L ratio greater than the other, that is more powerful. So tell me which should be stronger? M1 should be stronger or M3 should be stronger? For a fast reading 0. M1 should be okay. M1 should be stronger. And why so? Yeah, CC to discharge fast. Yeah, that is correct. So M1 should be stronger as you are saying, right? But what if M3 is stronger? If someone has not taken care of it and M3 is stronger? What will happen then? No. Something, capacitor will discharge slowly. That is there. So what will happen is, see here. This voltage node is 0 volt, right? Right now it is 0 volt. Yes or no? Hello, yes or no? If M3 is weaker, as you said, the discharge will be slow. So some charges may get accumulated at node Q. So that means voltage at node Q might rise because it should pass. It's a pass transistor, no? It should pass logic, whatever logic has been applied over here. Yes or no? And here it is 0 right now. So some charges of the capacitor might store at node Q. So V of Q, sorry, V of Q may rise. The voltage may rise. And if this voltage is greater than the threshold voltage of the next inverter, then the inverter voltage will change. Yes or no? Are you understanding? See, if this voltage at node Q is greater than the threshold voltage of M2, let's say, बराबर है? So if this voltage here, let's say this voltage is V1, this node is V1. So let's say this voltage at V1, maximum voltage, it's not 0 now because it's M3 is weaker and M3 is stronger and M1 is weaker. So it's not pulling down so fast. So if, let's say, if someone is not designed properly, M3 will allow some charges to build up at Q. So V of Q or V of 1, if this voltage is greater than the threshold voltage of 2, okay, अगर ये M2 के threshold voltage से ज़्यादा है, so M2 can turn on, ना? Yes or no? So if M2 turns on, then the output will be 0. It will be a wrong logic. Yes or no? So that will lead to incorrect operation. This is called as destructive read. This will reading it. The data has been read, but it's destructive data. So data read operation should not destroy the stored information. Yes or no? So this is called as destructive data read operation. So if V1 is greater than VT2, then we can call it as, let me just open it again. I hope it will come properly. Yeah. If V1 is greater than VT2, then QB can switch the state. The second inverter can switch the state. Yes or no? And that will lead to a wrong data. So this is called as destructive read operation. Destructive read means already stored data is getting disturbed. So first condition over here in the design requirement is it should be non-destructive. Okay, and we can modify the stored data during the write phase. These two conditions should be satisfied. So for this, to prevent this, what should happen? What you should do, as you told initially, make what stronger? M1 stronger, no? Yes or no? And M3 weaker. Yes or no? That means W by L of 3 should be less than W by L of 1. Is that correct? मतलब make a stronger pull down. Are yes or no? If you do this, then there is no chance. Maybe some charges are stored, so this will pull it down. So it will not allow this condition to occur. ये condition आएगा ही नहीं. Because M1 is stronger, it will pull it down very, very fast. So read access also will be faster, and this condition destructive read will not be allowed. All right. So basically, this is what it means. Then there is something called as a bit cell ratio. We can write it down. Bit cell ratio. It is called as beta. It should be W by L of 1 divided by W by L of 3. Okay. For the other transistor also you can write W by L of what is the other transistor? 6 upon W by L of W by L of 4 upon W by L of 6. ठीक है वो रहने दो, but this is what the ratio should be. It is written over here also, right? W by L of 3, that is M3, should be less. And where this condition comes from? Here it's saying that I3, current I3 is almost equal to I1. Okay, so यही condition लिखा है देखो, V1 max should be less than or equal to VT2. Should not turn on M2 transistor. Else what will happen? Destructive read will happen. Are you understanding? So for it to be non-destructive, this condition should not be satisfied. So this condition should be taken care of year over year. Okay. Understood? So M3 should be stronger. M3 should be in saturation, where M1 should be in linear. So M1 should be stronger basically. So we can equate these equations and we can get the condition. But basically what we can say is bit cell ratio should be less than 1. This should be less than 1. Sorry, it should be greater than 1. Sorry. This should be greater than 1 always, bit cell ratio. then only this condition will not be satisfied. So these are the conditions. You can go through it. It is Kn VGS minus VTN the whole square because it is in saturation, right? So M3 के लिए VGS is VDD minus V1, okay, minus VTN, and it is in linear region, so twice VGS. So for M1 VGS is VDD, okay, minus VTN minus V1. VDS is V1, okay, VDS is V1 minus V1 square. So if you rearrange the terms, you will get this equation. Kn3 upon Kn1 is W by L of 3 upon W by L of 1. And that is actually bit cell ratio. Did you understand or no? Because नहीं तो ये trip point ये change हो जाएगा. So if this trip point changes, if Vin becomes, let's say, here V1 becomes greater than VT2, and threshold voltage of VT2 is 1 volt. So if this become 1 volt, it will change the state. Okay, because this goes as input, so this will change the state, and that will lead to a destructive read. We don't want that. Understood this design strategy? Hello. So here these are all from Kang. You can read from there. Okay. So you have to keep W by L ratio of 3 compared to W by L ratio of 1. What you should keep? 1 should be greater than 3. Okay. Yes or no? So for a data read operation, to guarantee that V1 does not exceed threshold voltage of M2 over here, so that M2 remains off during the read phase, we keep V1 max less than VT2. Alright. And yeah, M3 operates in saturation, M1 is in linear, we can equate this. So if this condition is followed, M3 will remain off. If you follow this condition which is given over here, M2 will remain off. It should remain off, right? Off during read 0 operation. So this condition should be followed. Got it? Now we go to the next one. Everyone, write 0 operation. Alright? Are you ready, everyone? So here it is Q, here it is Q bar. So initially here Q is VDD and Q bar is 0. Okay. So what do? We have to write a 0. So bit line we make it 0 and bit line bar we make it VDD. This is basically bit line, this is basically bit line bar. Okay. And word line is also VDD. So here it is, you can see word line is VDD. Yes or no? This is VDD, this is 0. This is storing VDD, this is storing 0. So if this is storing VDD, then M5 will be on and M1 will be off. If this is storing 0, QB is storing 0, so M6 will be off, M2 will be on. Agree? So this voltage over here will be storing VDD. So this is like VDD, and this voltage over here will be 0. So this is like 0. So M5 and M2 are also on. Okay. Now tell me what is the problem over here. Tell me how will you explain this? Which should be weaker, which should be stronger, or what will happen over here? Come on. You're writing 0 into it, right? So that means Q should become 0. Hello. Yeah, tell me what will happen over here. Yes. Acha. Here I'll tell you the problem. The problem is that yeah. So M5 is on. So node Q is precharged, I mean is charged to VDD via VDD with a VDD voltage. Now since this access transistor is on and this is 0, and we know here we have a capacitor over here, see bit line. So what will happen is this will discharge like this, and node Q should become 0. Okay, if it becomes 0, that means you have written 0 into the cell. That is perfectly fine. Now for this to happen, which transistor should be stronger, M5 or M6? Tell me, M5 should be stronger or M6, M3 should be stronger, sorry. M5 or M3? No, no, no. Here M5 should be stronger. Why M3 should be stronger? Here you can tell me, yeah, correct, correct. M3 should be stronger. Why? Because here if it is VDD, it will pull it down very very fast to 0 if this is stronger. So here what we can say, M3 should be stronger compared to M5. Okay, so W by L of 3 should be greater than W by L of 5. Agree? So if that is the case, then this node voltage Q will be immediately, very fast pull down towards ground. And if that pulls down towards ground, we have a right 0 written already. Okay, into the circuit. Similarly, if this becomes right 0, this becomes 1. Okay, how this becomes logic 1? Tell me. How QB becomes logic 1? Because this is CBLB. So what is happening here now? QB will become 1, and so this will charge, right? Well, what will happen over here? Tell me. Here it will charge or it will discharge, or what will happen? Charge, right? Like this. Yes or no? It will charge the capacitor to VDD. So this voltage will increase to VDD. This should become VDD and this should become 1. This should become 0. Okay, this will change, then only the data will change, right? But what is the condition to avoid over here? What is the dangerous condition? The dangerous condition is if voltage at Q does not fall to 0. If voltage at Q does not fall to 0 means what? What does that mean? No, 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 no. M5 nahi, M5 nahi. So if this voltage falls, does not fall below this, that means देखो ये VDD होने के लिए M2 should be off, right? For this to be VDD, this is 0, right? So for this to be VDD, M2 should be off. When will M2 will be off? Whenever V of Q or V1 is less than VTN2, yes or no? बराबर ना? Then only M2 is off. Is M2 is off, then only QV will become VDD. Agree or no? But what if V of Q equal to V1 is greater than VT2, has not fallen below to 0. It has, let's say the threshold voltage is 0.7. Let's say this is 1 volt only. मतलब ये M2 on ही है अभी तक. So if M2 is on, it will lead to incorrect output. Yes or no? So that is the problem. Understood the problem? So if this is on, M2 is still on. M2 is still on, and that is a problem. So that's why V1 must be kept reduced to below VT2. So that's the condition which should apply. V1 should be less than VT2, so that M2 becomes off and QB changes the state. Okay, that means V2 rises, V1 falls. This should happen. And again the condition, it's written over there. It's clearly seen, and this is called as a pull-up ratio. pull up ratio PR, that should be equal to W by L of phi upon W by L of 3, and this should be less than 1. That means W by L of 3 should be stronger than W by L of phi. That care should be taken. So if you follow this table, if you follow this formula, so basically in order to change the stored information, that is to force V1 equal to 0 and V2 to VDD, the node voltage V1 should be reduced below the threshold voltage of M2 transistor so that M2 turns off first. If M2 turns off, then the voltages are proper. Alright. So if this condition is satisfied, if the box condition is satisfied, then we can say again this is like a linear and saturation condition. M3 is in saturation and M5 is in M3 is in linear and M5 is in saturation. So it is Kp by twice VGS minus VTP the whole square, and this is in linear. So you can equate this, you can solve this, and you will get this condition. And if this condition is satisfied, M2 will be forced into cutoff mode during write 0 operation. Understood? So these are called as the design strategies. Okay, so this will guarantee that M1 turns on subsequently, changing the stored information. So here means if M2 turns off, then M1 will turn on, changing the stored information. Hence we have written a write 0. Okay, understood this? Understood about the write 0 and this design strategy of SRAM cell, everyone? You can read more from the Kang book. Yeah, you can ask anything. Anyone has any doubt? Yes, no, tell me first. Okay, great, great. So this is how the SRAM cell looks like. Okay, these are the bit lines and these are the word lines. If I connect in an array, understood? So symbolic form is used. That is this one. This is a symbol of an inverter, and then we have the excess transistors like this. Okay, this is word line, and these are bit lines, bit line and bit line B. So this is one 1T SRAM cell. I mean, sorry, not 1T, 1 bit SRAM cell, 60 SRAM cell this is. Okay, so this is an SRAM array which I wanted to show you all. Now we'll talk about SRAM write circuitry. You remember a write operation is performed by forcing either a BL to logic low level, yes or no, or BLB to logic low level. So to accomplish this task, we have to connect a certain connections in the circuitry. So let's draw the SRAM write circuitry. Everyone please draw it along with me. So you have over here what are these things? These are pull up transistors. Okay, then comes the SRAM cell. So I'm drawing the SRAM cell in blue color. I'm drawing a little small for a reason. You will understand now. This is one SRAM cell. Okay. Let me expand it a little. So these are word line and these two are bit line. These are columns actually. We can call it a bit line or C column, or bit line bar or C bar, whatever we want to call it. Okay, so this is my 60 SRAM cell which I'm put in inside the box, this one. Okay, and many such cells can be followed. So this is 1 bit SRAM cell. Okay, now right circuitry is an external circuitry. It is connected externally like this. So we have two transistors over here, one and then second one, M1, M2, and there is third transistor over here, M3, and this will come from the column decoder, whichever column is to be selected. All right. Now over here we can select it like this. This is a two NOR gates are connected. Yeah, right circuitry, it's a little bit tedious. Okay, and this will come over here. This will come over here. This is W. This is data. All right. And this can be given to multiple columns. So here I have shown only one, two, three, four. So this is WB and this is WB bar. Okay. So draw this circuitry. This is my SRAM. Above circuit is fine, right? Below only I'm drawing it again. So it is M1, M2 and M3. W bar, data, and WB, WB bar. I'll explain them. No worries. So here we have, let me keep a check on time also. Yeah, we have half an hour more. So here we have W bar, data, WB, WB bar. So this is 001, 10X. This is 100, 010. Okay. And here the operation will come. All right. In this case, are you all ready? Can I explain here directly? Everyone? Hello? Okay, let me explain it over here. Here I've already drawn. So here the outcome I'm writing. Here VC bar will be low. Here VC will be low. Here both VC and VC bar will remain high. Now let me explain you how. Okay. So here M1 and M2, M1 and M2, M1 comma M2 are used to pull down the two column voltages C and C bar. Okay. So used to pull down C and C bar to ground, while M3 completes the conducting part to the ground. So M1 via M3. So M3 should be also be on, and when M2 is on and M3 is on, it will conduct their part to the ground. Okay. So are the pull down C and C bar. M3 is driven by column address decoder circuitry. That means M3 turns on only when the corresponding address is selected. So M3 turns on only when the corresponding address is selected. So M1 and M2 are both called as column pull down transistors, or these are also called as bit lines, columns or bit line bar. Okay, so column pull down transistors. All right. M1 and M2 are driven by WB and two pseudo complementary control signals. So these are controlled by WB and WB bar. Okay, these are pseudo complementary signals. Okay, WB and WB bar. Now, write enable signal. W is write enable signal, which is active low, and the data to be written is data, are used to generate the control signals as shown below. Okay, now we have to see this and then we have to see the operation. So M1, M2 and M3 must have sufficiently large W by L ratios so that the column voltage must be forced to almost zero level during a write operation. Okay, so M1, M2 and M3 should have large W by L ratios so that during the write operation, during a write operation, the column voltages can be forced to zero level. Okay. The data input circuitry, the write circuitry consists of two NOR gates. So NOR gate number 1, NOR gate number 2. Okay, and this can be shared by various columns. So this is only stored in one column. It can be shared with various columns. Several columns, assuming that one column is activated by the column address decoder at any given time. Okay, now how does this operate? Now tell me, when W bar is 0, that means this becomes 1, na? Correct or no? W bar is 0, this is 0. This is a NOR gate, right? What is the symbol of a NOR gate? A plus B bar. So 0, 0, 1, 1, 0, 1, 0, 1. What is the output? 1, 1, 1, 0. Yes or no? Hello? Are you listening? Okay. So when the data is 1, and this is 0, what is the output over here? 1, right? When this is 1, this will be 1, right? Yes or no? So M2 is on and M1 is off. Or no, or something else is there. Just check. So W bar will be active, means W bar will be 0. So how to check? Please check it. So this is just the data write circuitry associated with one column pair in a SRAM array. This is just a one column pair. So how to explain this? Just tell me. So when the data is 1 and this is 0, W bar is 0. That means this will be 0 or 1? 1 or 0 it is, tell me. This will be 1, this will be 1. So this will be 0, right? And this is 1 and 0. So this will be 1. So M2 will be on and M1 will be off, correct? So if this is on, and let's assume that that column is selected. So my C bar will be towards 0. Yes or no? So VC bar is almost low. Agree? Now let's go to the next one. Again W bar is 0. So this is 1 and 1. And data is 0. So this will become 1, right? And this will become 1 and 1 again 0. Yes or no? So M1 will be on now. And the C will be towards ground. So VC will be low. Agree or no? Now when W bar becomes 1, that means it is 0, 0 here. Here it is 0, here it is 0. Irrespective of the data, what will happen? If here it is 0, irrespective, this will be 1, this will be 1. Oh, sorry, this will be 1, right? Irrespective of data is 1 and 0. What will happen due to that? This is 0, 0. So what will happen over here? Let's say this is also 0. So this becomes 1. And what happens to this? Let me close this out. Yeah, tell me what will happen when the data, I mean the W bar is 1, that is inactive. If the write enable is inactive, it will not write, and both the transistors will remain off. Okay, and both the columns will remain high. If these are off, that means it will pre-charge to VDD, YD pull-up transistors. So this is your data write circuitry for SRAM cell. Okay, got it? Everyone? Yes or no? Okay. Now, see, we have talked about many times. We have drawn the 60 SRAM cell, and we talked about something else which we call it. This is pre-charge. Pre-charge means this phase. This is pre-charge, and then comes the 60 SRAM cell. You remember this one? I am drawing it shortcut now. Okay. This is word line. This is bit line. This is bit line bar. Alright. And what did we say? This goes to a sense amplifier. Yes or no? This goes to a sense amplifier. And the sense amplifier output will be the data out. So what does the sense amplifier do? If BL is greater than BL bar, it will produce out logic 1. And if BL is less than BL bar, it will produce logic 0. That is what we have assumed, right? So this sense amplifier is nothing but SRAM read circuit. So that will read the data from this SRAM cell. This is a 60 SRAM cell. Yes or no? So this is where the sense amplifier is. And we are going to study sense amplifier. What is a sense amplifier? Sense amplifier is normal differential amplifier only. So we have studied differential amplifier, right? In your syllabus? In your lower syllabus, right? Yes or no? So this is your differential amplifier. We can connect this is nothing but sense amplifier only. Huh? So here we have BL, voltage BL, and this is voltage BLB or BL bar, whatever we can call it. So here we can check the output VO1, VO2. Okay, so this is single source coupled differential amplifier, DFAM, for read operation, or it is also called as a sense amplifier. So during the data read operation on the SRAM array, the voltage level on the either of the columns, which is BL and BLB, drops slightly slightly after the pass transistors are turned on. Access transistors are turned on by the row address decoder circuit. So aim is to reduce the read access time. That's why we go for a sense amplifier. So the read circuitry or the sense amplifier must detect a very small voltage difference between the two complementary columns, which is BL and BLB. Okay, and amplifies this difference to produce a valid logic output level. So let me write over here, the read circuitry or sense amplifier must detect small voltage difference between BL and BLB and amplify this difference to produce a valid logic output level. Okay, that's the functioning of read circuit or a sense amplifier, and these are directly one and the same thing. Okay, understanding? So the gain of the differential amplifier can be improved if we use a active load over here. That means instead of resistors, if we use another MOSFETs, it can be significantly increased. So that means it will become more sensitive. That means a smallest change in BL and BL bar can be detected by the sense amplifier. So this is your simple SRAM read circuitry. Now ID1 and ID2 is given by these formulas. The small signal will reveal that differential gain will be given by minus GM into R. You have studied this in the low semester, right? So if you want to increase the gain, increase R. Yes or no? But increasing R will cost more silicon area. So the solution is to replace this R with an active load. And GM will be given by, either you can increase GM by increasing ID. But if ID increases, your registers also will change. So this is the basic idea. This is the basic function of a sense amplifier. Okay? Yeah? So this circuit will perform the task of a basic sense amplifier and produce the output. What is a differential amplifier? Differential amplifier means it will amplify the difference between the two inputs. Yes or no? So these are nothing but VBL and VBLB. Same thing, or you can call it VC or VC bar. One and the same. Are you understanding or no? Read circuitry is understood? Okay. And what it do is it also increases the access time, the read access time. So it will sense the difference between the two bit lines and immediately give the data output. Now single stage differential amplifier without the resistors will be as follows. So please draw this circuitry. This also you might have studied. It's a current mirror circuit. I don't know, you all had it in your syllabus. Whether you have studied or no, I don't know. So this is your same, another version of sense amplifier. This you can call it as a clock. This is M3. This is your bit line bar. This is your bit line where you're connected the capacitors CBL, CBLB. Okay. This is M4, M5, M2, M3. So this is current ID1, this is current ID2, and this is current ID3. So ID3 should be equal to ID1 plus ID2. Alright. And this is the output. It's further given to an inverter so that the logic is restored. So this is the data output. Okay, this is the sense amplifier. This is called as differential single stage differential current mirror sense amplifier. And what's the job of this? This single-ended output. We have a single-ended output. What's the job of this? To amplify the difference between BL and BLB and produce at the output. Okay. So two NMOS transistors M1 and M2 are connected to the bit lines BL and BLB. Each bit line is represented by a large capacitor CBL and CBLB. NMOS transistor M3 is act as a current source for both the branches and is controlled by a clock signal. So the output inverter, this is inverter. It's not a part of differential amplifier, but it is used to drive the output node. So before the beginning of a read cycle, the two bit lines are pulled up for equalization. So these capacitors are pre-charged to VDD first. And then when the clock is low, M3 becomes off. Since M2 and M1 and M2 conduct, the common source node is pulled up and the output node of the amplifier also goes high. Okay, so due to that, if one of the BL and BLB comes down, it will sense it. The sense amplifier will sense it, and it will amplify the difference at the output. Okay, and this data out will drive the output node. So once the memory cell is selected for read operation, the voltage at one of the bit lines will start to drop slightly. So at the same time, clock signal is selected. And if the stored data selected on the selected RAM forces BL or BLB to go slightly below. So let's say BL signal slightly drops. So M1 transistor turns off and the output voltage uh, of the differential amplifier drops immediately. Therefore, the output of the inverter goes high. Matlab, what they are saying is, if BL is less than BLB, so M1 voltage will be lesser. So that will means M1 will be off and the output will be low. So data output will be high. Okay, and if the stored data on the selected SRAM cell forces BLB to drop slightly. Now if BLB is low compared to BL, what will happen? M2 will turn off. So therefore output of the differential amplifier remains high. That means inverter will preserve its logic low output level. Now, alright everyone. So this is your sense amplifier. Come on students, yes or no? Last few minutes. I know it's a little bit at the later end, but this is how the sense amplifier is. So we are covering both the topics, sense amplifier and data read circuitry. So there is one more version which I'll show it to you just. So this is my sense amplifier which I've just talked about. You can refer its this thing theory in the ebook of Kang. Now this is two-stage differential amplifier. I'll recommend do not study this for the exam. This is to further improve the read access speed. That's it. That's the only advantage of it. So you can go through this. Now you can see the response time of a two-stage output. It's much better and much faster. So that's the advantage you get for a two-stage sense amplifier. Okay. We have another type of a sense amplifier which is called as a NMOS sense amplifier. So again, it's a cross-coupled latch. We assume that both BL and BL bit line and bit line bar are pulled up to VDD during the pre-charge phase. Okay. So let's say both are pre-charged to VDD. Now we'll consider, now I'll explain it here only. Now let's say that when the access transistors are turned on, now remember this is a sense amplifier. So sense amplifier gets activated whenever the access transistors are turned on. Okay, I hope you remember. So let's say this VC voltage starts to drop down. Okay, when SRAM access transistors are activated. So now what will happen? Let's say the clock is also applied and M3 is on now. M3 is on. So this V3 is slightly below. This drops and this voltage almost remains the same. So this voltage remains the same as the pre-charge value VDD. And this voltage drops. So we can say VC bar is greater than VC. Okay. So M1 turns on first. If this voltage drops, then M1 turns on first and further pulls down the voltage. So M1 when it turns on, it will pull down the voltage further, this voltage further. Yes or no? So it will pull it down. So now what will happen? This pull down voltage will be applied. This is VDD. That means this is turned on. Now this voltage falls down, right? This voltage falls down. So it will be difficult for M2 to turn on. So M2 turns off completely. M1 is still on. So BC is discharged via M1 and M3. Okay, so this is how the operation takes place here. So in most of the SRAM arrays, cross-coupled sense amplifiers are used in conjunction with the differential sense amplifier. That means this is also used together along with the sense amplifier which we have studied over here. This one. Now, the cross-coupled sense amplifier amplifies the difference, small voltage difference between already existing two bit lines. This voltage difference must still be translated to a logic level. Okay, so whenever, now this is the complete read and write circuitry. You remember this is my 60 SRAM cell, these are my pre-charge transistors, this is my SRAM sense amplifier, this is my CMOS cross-coupled sense amplifier, and this is my data write circuitry. So together, all the things together. So this is a complete circuit of CMOS SRAM 60 cell along with the data write and read circuitry. So here cross-coupled sense amplifier serve as a front-end structure to amplify the small difference between the two bit lines. Whereas the differential sense amplifier detects the voltage difference and generates the appropriate output level. Okay, so there are two sense amplifier over here, sense amplifier number 1 and 2, and there is one data write circuitry which is here. So this is the write circuit, and these two are the read circuits. So this is how the overall SRAM structure will operate along with the read and data write and read circuitry. And yeah, that's the end of today's topic. So you can go through it. I mean, they might not ask you to gather this entire structure, but this is all we have covered. So you can go through the theory of it from the Kang book. All right. Now you can ask your questions.